Question number 12 from the exercise. For the wave on a string described in exercise 15.11, that is the previous question we saw, do all the points on the string oscillate with same frequency? So there is some standing wave created on that string, correct? That's what we have learned. Okay. So now the question is, do all points have same frequency? Yes or no? Will all points on that string, and this string will be having a standing wave, will all points have same frequency? Yes or no? What do you think? Will all points have same frequency? Yes or no? Okay, the answer is yes, same frequency. Reason, if you would look at equation of oscillation for all the points, suppose it is 2a sin a x cos omega t, right? For a standing wave, this is the equation. Will have different amplitude, but omega is same. Again, let me make you recollect. Earlier we have learned that frequency depends on source, not on medium. Do you remember that? Everyone, frequency depends on source, not on medium. Alright? So all points will have, yes, the same frequency. Yeah. Along with it, I want you to answer that question which I left for you last time, D, from 11. Okay, we will need that here, I think, later on, in B, C or D part. Can you tell me what answer you got for D? Which harmonic does this string oscillate in? Did you find it out? Which harmonic does the string oscillate in? Okay, I've got a few answers. Let's see. First of all, it is to find, we have to find the frequency again. So I think you would have done that. F will be equal to omega by 2 pi, right? This is 120 pi by 2 pi, that is 60 hertz, is the frequency of the wave. Right? 60 hertz is the frequency of the wave. Now, what is fundamental frequency of string? What is the fundamental frequency of string? How to find that fundamental frequency of string? What's the formula? Fundamental frequency of string. You could call it F0 here to separate it from F. Okay, what is fundamental frequency of string? No, Ankita, not correct. Fundamental frequency. Not correct. See, some of you have answered this wrong. Some of you are saying NV by 2L. No, wrong. Fundamental frequency is only V by 2L. Is that clear? Fundamental frequency is V by 2L. And general formula of resonant frequencies is NV by 2L. I hope you see the difference between them. Fundamental frequency is one of the resonant frequencies. I repeat, fundamental frequency is one of the many resonant frequencies, right? 1V by 2L, 2V by 2L, 3V by 2L, 4V by 2L, all these are resonant frequencies. Out of that, the smallest one, the first one, 1V by 2L, that is also called fundamental frequency. Okay, hopefully there will be no confusion about this in future. Alright? Okay, so fundamental frequency is V by 2L. right? So have we found out V? That was a part of the question, I believe. What was speed of the wave? What was speed of the wave? $180, $120, $180. Why are people getting different answers? $60. બધાને આન્સર સ્પીડ નો આવે તમે લોકો ચેક કર્યો તો કે નહીં પાછળ બુક ના આન્સર સાથે મેચ કર્યો. V is omega by k. Okay, so what's omega? 120 pi upon k is 2 pi by 3. So this is V divided by 2L, 2 into length. What is the length? 1.5 meter. Okay. So here this cancelled, right? This cancelled again. So 20 by 3. I say fundamental frequency is 20 by 3. Is that okay? Right? So speed was 60 into 3, 180. Yes. Speed was 60 into 3, 180. Yes, that's right, 180. So 20 by 3 hertz is fundamental frequency. Isn't it? 20 by 3 hertz is fundamental frequency. Is that clear? No. I made a calculation mistake, is it? Let's see. Okay, let me just do it again. First of all, V, omega by k, omega 120 pi upon k is 2 pi by 3. So 3 will go in numerator, 3 into 120 pi by 2 pi. So this is 60, so 180, okay. So this is 180 upon 2 into 1.5. Alright? 180 upon 2 into 1.5. I made a calculation mistake. So this is 180 upon 3. So that is 60 hertz. Yes. Same as frequency of the wave, isn't it? So the wave has same frequency as fundamental frequency. Okay or not? Okay? Wave has same frequency as fundamental frequency. What does that mean? What does that mean? This is vibrating in first harmonic. Clear? This is the first harmonic or fundamental frequency. Alright? Okay, so keep that in mind. Right? Keep that in mind. Let's go to 12th part B. Thank you. Now the question is, are all points vibrating in the same phase? That is, do all the points have same phase? Yes or no? Do all points have the same phase? For deciding this, we should try to draw or picturize what is going on. What is given is, we know that this is fundamental frequency. So of course this is a node, this is a node. Is there any other node in between? Is there any other node in between? If yes, how many? How do we know? That's where the diagram comes into the picture. That's why I was telling you, draw diagrams. That helps. What was the diagram for fundamental frequency looking like? Do you remember? It's just like this. Yes or no? Yes or no, everyone? Do you also remember this kind of oscillation from that video as well? Right? Do you also remember this kind of picture from that video that we saw? Only one looping form. Okay, so only two nodes are there, right? Only two nodes. So all points between two consecutive nodes oscillate in the, what was the sentence? All points between two consecutive nodes oscillate in Come on. Yes, in the same phase. So do all points have same phase? Yes, again. Right? Okay? Just like I told you earlier, it's that what will happen is that if this is the string, the point over here, when it goes up, this point will also go up, this point will also go up, this point will also go up. Then they all will come down. So their motions are synchronized. Their motions are always occurring together. Right? They are all in the same phase. I hope that is clear, everyone. I hope you found that line from the notes. Did you find it? We have mentioned it. All points between two consecutive nodes are in the same phase. What lambda by 3? What are you talking about, Raj? How did you get lambda by 3? Next, do all points have same amplitude? What do you think? Do all points have same amplitude? No, wait. Raj, everything fits to the picture completely. Think about it. Wavelength is 3 meter. Okay, wavelength is 3 meter. In the first case, means in the fundamental case, do you realize that we should have this relation? And we have that relation, don't we? Isn't 1.5 equal to 3 by 2? So everything is proper. It is all proper for fundamental frequency. You may have calculated this way. Alright. Explain your answers. We have already gone through everything, right? Then, second part. What is the amplitude of a point 0.375 meter away from one end? Okay, let me just clear up this diagram and draw it again. So the question says that if there is a node here, there is a node here, both are tied, then at 0.375 meter from here, okay, there will be some point, this one, let's say P, which is oscillating. So where P oscillates, we have to find amplitude of this point. Okay, so in standing waves, what is equation of amplitude? A dash, What will be amplitude for standing waves? What will be amplitude for standing waves? Yes, 2a sine kx, not sec x. Alright, the way I have written this looks like sec x, but nevertheless. So 2a, what was a? Go back through question 11. What was a? Hurry up, please. Hurry up, everyone. What was a? Was a 0.06 or 0.03? Be careful. This is one of the common mistakes. Was a 0.06 or 0.03? No, 0.03, right? 2a itself is 0.06. I hope that is clear. And sine k, sine k, we already have value 2 pi by 3 given in question x. What is x? 0.375. Okay, if I write 0.375 in fractions, it will become 3 by 8. I repeat, 0.375. I have written it in fractions. It becomes 3 by 8. Clear? Alright, I have just put value. Now we just have to simplify this. So we have everything. 0.06 into sine pi by 4. Sine pi by 4, that is 45 degrees, right? Sine 45 degrees 1 by root 2. You divide this and you get your answer. Understood the method? remember earlier about the chapter waves, I told you that waves is one chapter where you should remember the formulas and some important sentences. Mostly you just have to put the formula and get the answer. But the confusion often will be which formula to use. Right? The concept is not complicated, but understanding the question and using the right formula, that's the main thing here. Right? You can see almost every time we are using sentences that we have written earlier. For example, do all have same frequency? I've already told you. Right? That when a wave is there, all points have same frequency as source. Are all points in same phase? For that we use the sentence about two consecutive nodes, right? And every point in between has same phase. Same amplitude, we have a sentence. About amplitude, we have this formula directly, we just have to put it, right? So like this, things are quite simple, but only if you understand what they are asking. Okay. Question 14, 1-4. No, we have done it, right? No, not done. Sorry, not done. Yeah, 14. Question 14 from exercise. Right? So, it says a wire stretched between two rigid supports. So, this is a rigid support and this is also a rigid support. So, this is basically a wire fixed at both ends, isn't it? Right? Familiar territory, right? We are used to this now. Okay, what does it say? It vibrates in fundamental mode with how much frequency? 45 Hz. Fundamental mode means this is actually the fundamental frequency. Clear or not clear? Clear or not clear, everyone? Question not now? It's given that, so what's happening is this wire is oscillating like this in standing wave with fundamental frequency. Okay, like we saw in that video. So now the mass of the wire is given 3.5 × 10⁻² kg and linear mass density of wire is given mu. Linear mass density is 4.0 10⁻² kg per meter. Okay. So first question is, what is the speed of transverse wave on the string? Okay, first question. Speed of the transverse wave. Alright. Okay. Can you tell me some formulas that have speed of transverse wave in it so that we could solve this and get the answer? Let's see which formula works. Come on. It's your responsibility. Hurry up. Look for formulas for wave speed. On V by 2L. V by 2L is wave speed. Yeah. F is V by 2. F is V by 2L. Okay, so some of you are suggesting this one. Okay, I am not saying this is right or wrong. I have not said anything. Some of you are suggesting we do F equal to V by 2L. We have F fundamental frequency. But what about L? What about L? Do we know L? Very good, Amrita. We can find L. That's right. If you will use V equal to √T by mu, do we know the tension? If you use V equal to √T by mu, do we know the tension? Ami, how will we find lambda? Okay, so this is the best choice. But first we should find out L. How to find L? Mu, mass per unit length, isn't it? Is this clear? So based on that, we can say L is equal to m by mu. We go and put it over there. So F is equal to V by 2m and mu will be in the numerator. Are these steps over here clear to everyone? Are these steps clear? Very good. So let's put all values so we can find B. Therefore, B is equal to 2mf upon mu. Alright? Okay, I've not done anything else. I've just multiplied and divided things here. Okay, you could go from here to here directly also. No big deal. So 2 mass 3.5 10 raised to minus 2, frequency is 45 divided by mu. Okay? Right? The rest is for you to complete. Hurry up, tell me what's the answer. Tell me what's the answer. Priyansh, ટેન્શન સુધી પહોંચી ગયો તું? કેમ બધાને આટલા બધા અલગ આન્સર? This will be cancelled. You have to multiply 35 with 45, 3.5 with 45 and divide by 2. Okay? I want a reliable answer. Come on, everyone. What's the answer? બધાના આન્સર અલગ આવે બોલો. યુનિટ અલગ આવે, કા વેલ્યુઝ અલગ આવે. કેમ આવું બધું થાય? જાદુ કરો તમે બધા. Can I trust you all? Most of you are saying 78.75. Most of you are saying 78.75. Is that okay? Meter per second. Alright. Okay. Fine. So first part is done. Now there's something else in the second part. We have to find tension. Right? In the second part of the question, we have to find out the tension. So what's the tension? How to find it? Easy part. Don't you think? T is equal to, just use the relation of speed with tension. Alright? For transverse wave, V is equal to under root T by T. Okay, so always do this yourselves. Okay, that's for you to complete. Now, let's go to question 16. Let's go to question 16. Okay, now this question 16, I think it's a little different, okay, not in terms of solving, only in terms of understanding. A steel rod 100 centimeter long is clamped at the middle. Okay, so first of all, let's draw this. So here is a steel rod. Okay, what's the length? 100 centimeter, which is 1 meter. And where is it clamped? Is it clamped at the end points? No, it's clamped at the middle. So it's possible that from upward there is one knife edge or some holding device, and similarly from bottom also there is a holding device. So it's clamped like this. Did you understand? Okay. Now it is given that fundamental frequency of longitudinal vibrations, notice that longitudinal vibrations, not transverse. Okay, fundamental frequency for longitudinal vibrations is given. How much? 2. Let's call this F0, 2.53 kilohertz. All right, you could call this F0 as well, right, for fundamental frequency. But just write F also, no problem. Okay, don't worry too much about the symbols. What is the speed of sound in steel? What is the speed of sound in steel? Okay, so we have to find what the speed of sound in steel. This is a steel rod. Okay. One big difference here, first of all, is this. Okay, one big difference compared to other questions is this, right? Okay, the other thing is that here this is not clamped at the end points, it's clamped at the middle. So let me draw the pattern of standing waves. Because this point here is clamped, it can't go anywhere. Do you understand what I'm saying? It's clamped, it's held like this. Let's say this is that rod, and this point here, it can't go anywhere because it is clamped. So because of that, this point is a node. Did you understand or not? Did you understand that? Why is that point node? Because it is clamped at the middle, right? So this point can't go anywhere. It has to be a node. Now, if we are talking about fundamental frequency, it should be the smallest number of nodes and antinodes possible, right? Smallest number of nodes and antinodes possible. So that's why the diagram of the standing wave inside this rod, okay, this is the same rod, shall be as follows. Did you understand? Clear or not clear? The diagram? Devers, I hope I have answered your question by the diagram. Why are endpoints not nodes? Why are endpoints not nodes? Because they are not tied, right? They are free to move. Do you realize they are free to oscillate? Okay? Is this fine? Right? So the endpoints will be antinodes and there will be just one node here. Okay. Now, in this case, this distance between a node and the neighboring antinode is lambda by 4, isn't it? And this distance is also lambda by 4. Alright? Okay or not okay? Right? Clear? So what should we have? We should have total length is equal to lambda by 2. Total length of this rod as lambda by 2. So now we can easily find out speed of wave. Let's do it. See, we know that now lambda will be 2l. If n is lambda by 2, lambda is 2l. Therefore, v equal to f lambda equal to f into 2l. Did you understand this step? V which is equal to f lambda will be f into 2l. Okay? So, how much is this? Therefore, V equal to F 2.53 into 10 raised to 3 into 2 into length. Length of the rod is given. Is length of the rod given, everyone? 100 centimeter. Yes, 100 centimeter. So, 1 meter, isn't it? 100 centimeter length means 1 meter. Right? So, that's your answer. 5.06 into 10 raised to 3 meter per second. Okay? 5.06 into 10 raised to 3 meter per second or 5.06 kilometer per second. Alright? 5.06 kilometer per second. Okay? You see, this is very fast. Do you realize this? Compared to speed of sound in air. Speed of sound in air is only about 330 meter per second under normal situations. In steel, the speed of sound is 5 kilometer per second, right? It's so fast compared to this. If you remember, I did mention earlier that sound behaves differently in gases and in solids, right? This is one part of that behavior, right? Sound travels very fast in solids, okay, compared to what it travels in air, right? Okay, right. Time for next question. So this was question 16. Right. Let's solve question 17. Okay, let's solve question 17. I'm using this one as well. A pipe 20 centimeter long is closed at one end. Finally, the closed pipe is here. Right? This is called a closed organ pipe. Which harmonic mode of pipe? Which harmonic mode? Okay, that's the question. At which frequency excited by a source? So suppose here you put a tuning fork of how much frequency? 430 hertz. Right? So basically, if you have a source of 430 hertz here, it will pass sound through this. There will be resonance, there will be standing wave. So you have to answer which harmonic mode. Okay, and the length of the pipe is given to us, 20 centimeters. Okay. Right? So let's do it by comparing it with the resonant frequency formula. What's the resonant frequency for okay, yeah, let's do it slightly different. Just one thing. Let's not do it like that. Here this will be easy to solve, just like basics only. So suppose find out fundamental frequency, because we only have to find harmonic. Find out fundamental frequency for this closed pipe. Come on everyone. Find out fundamental frequency for this closed pipe. Fundamental frequency. Remember, fundamental frequency means the first case. The smallest resonant frequency is called fundamental. How much will it be? Formula is right. V by 4m. The formula is right, everyone. V by 4m. So how much will it be? Is speed of sound given in question? Yes. 340. We are given that speed of sound in air is 340. So how much is this going to be? Okay, others, hurry up. How much is fundamental frequency? 425 hertz is the common answer that I am getting. Okay, 425 hertz. Right. Now, if fundamental frequency is 425 hertz, what do you think this is? This is 425, and the frequency of the source is 430 hertz. Is it an exact match? Yes or no? Is it an exact match? Yes or no? No, agree. But it's fairly close, isn't it? It is fairly close. Yes or no? Right? Okay. So you could really say that it's approximately, you could say approximately close to the first harmonic. All right. Okay. What this means is, this is not a perfect or the most ideal case of resonance. It's not like that, right? So here amplitude will be high, but not that high. I hope you understand what I am saying. Amplitude will be high because it's still fairly close, but not very high, right? That is, if these would be exactly equal, the amplitude would be the highest possible. You understood what I am saying? Okay. Frankly speaking, if you are very strict about it, I would say no, this is not harmonic. If you are strict about it, right? But like I said, this is approximately the first harmonic, but strictly speaking, it's not harmonic. Alright, I hope you have understood this. Do not get confused, okay? Don't worry too much about this kind of behavior. Right? It is close to the first harmonic, but not exactly first. Okay? Now, there is another part of the question. It says, will the same source be in resonance if both ends are open? That is, instead of this end being closed, suppose that end was also open. What if this end is also open? Both ends are open. Then what will be the fundamental frequency? If both ends are open, what will be the fundamental frequency? No, then also Mavi, you would not get exact answer. You can try. Without rounding off, you will not get it exactly. Yes, we get V by 2N. Okay, it will be double compared to this. I hope you realize that, because this is divided by 4, that's only divided by 2. So without worrying about any calculations, we can say this is going to be 850 Hz. Right? Now this is 430 Hz. This source 430 Hz. And this is 850 Hz. Do you think resonance will occur? Is 430 Hz in the list? Is 430 Hz in the list of the resonant frequency? This is the fundamental frequency, the first one. After this, you will get 2V by 2N. So that would be double. That would be 1700. Do you realize that in this list 430 can't be there? Okay, that's why no resonance. Clear? No resonance. Okay. Now let's I think we have done almost all questions of resonance. 15, yeah. 15 is remaining. Do we have time there? We will be able to. Okay, 15th question. Right, I am erasing all this up. Question 15. Okay, let's read. A meter long tube open at one end with movable piston at the other end. Okay. So what's given is that here is the tube. Okay. Right, let's say it's open at this end, and over here there is a piston that we are free to move inside this, right? So this piston can move back and forth. Did you get it? Okay, piston can move back and forth. So obviously, if this piston starts to move towards left side, the length of air column inside this will decrease. Correct or not? I'm just writing it here so that you understand the concept properly. Piston moves left, then length will decrease. Yes or no? Okay, because piston will block that much portion. Piston will block that much portion. Fine, that's clear, everyone. So keep this in mind. I'm erasing this sentence here. Now, it says that a meter long tube open at one end, so this is 1 meter long, fine, shows resonance with a fixed frequency source, which is a tuning fork of frequency. So here at the open end we are putting a tuning fork of how much frequency? 340 Hertz. So that's the frequency of the source. 340 Hertz. That's the tuning fork, right? When the tube length is 25.5 centimeter or 79.3 centimeter. So it's saying that we get resonance with this source. We get the tube in resonance with this source 2 times. First time when the length is how much? 25.5 centimeter. Whose length? Air column's length, tube's length basically. Piston can move till here, right? So second time we are getting resonance if this is 79.3 centimeters. Okay. Estimate the speed of sound. Estimate the speed of sound in this measurement or by this experiment. Okay, so how much will be the speed of sound in air? That's what we have to find. Now, here you see there are some words mentioned. It says edge effects may be neglected, right? Edge effects may be neglected. So first of all, we will understand what is meaning of edge effects, right? It's that you see in real, okay, what we have studied so far has been ideal behavior for pipes also. In real or in practice, due to the narrow diameter, I repeat, due to the narrow diameter of a pipe, think of a flute, let's say, right? Flute is not like a giant pipe, isn't it? It's narrow. Okay, so such pipes which are not that broad, right? The diameters are not very big. Okay, what happens in these kind of pipes is that the node, suppose this is an open pipe. Suppose this is an open pipe and this is open end. Then we have studied in ideal case, we have said that node is here. Do you remember that? Exactly at the end point of the pipe in ideal case, right? But in real, it's not like that. Okay, experiments have confirmed, basically this is something completely practical. Experiments have suggested that nodes should not be here. The node will be a little bit outside the pipe. Okay, so basically the wave is reflected back not from here but from a little bit outside the pipe. Now this happens only at open end. Okay, so in real or in practice, nodes are a little distance outside the pipe, outside the open end of pipe. Okay, this is something that can only be verified experimentally. Okay. So this is what makes us right that instead of considering, listen to this carefully, suppose there was a closed pipe, then instead of considering this node and this is anti-node, and when we do all the calculations, earlier we took only this length, do you remember, as this length as lambda by 4, but now in reality this length will not be lambda by 4 because node is here. So up to here is lambda by 4. Did you understand? So I am saying that lambda by 4 is not just L. It's a little bit more. Did you understand this equation? I am saying that lambda by 4 is not just L. It will be a little bit more. Why a little bit more? Because the node is here and anti-node is here. It's not here anymore. If it is here in ideal case, then this length is lambda by 4. But now the node is not here, it's over here. little bit extra. So this is that extra. That extra is written as E for end correction or end effect. Okay, this is called end effect or edge effect also, like this book uses the word. Okay, all these things mean the same thing. So you have to do this for all open ends. You have to do this for all open ends. This is something which is not even given in the book. Okay, point me out if it's wrong. Okay, frankly, I've gone through the book several times, but I've never found end correction or this explained anywhere in this text. But this is how it is supposed to be, right? So because of this, what happens is the formulas that we are writing. For example, when we write 2n minus 1 v by 4l, that can't be l anymore now, because lambda by 4 is l plus e. So here, do you realize that we should write l plus e? Yes or no? Nothing. At antinodes, there will be no change. Never. Okay, at antinodes there will be no change because the pipe is closed here. The air can never go on that side, right? So the sound wave must definitely come back from here. Understood? So there is nothing extraordinary at antinodes, it's only at the node. Alright? Okay, so like this it is for open pipe as well. Right? This is for closed pipe. Similarly, for open pipe also you can write it as NV by 4 L plus E. Okay? But this E and this E may not be same because these are different cases. I hope you realize. One is for closed pipe, one is for open pipe. Right? So this E and that E may not be the same. So this is called end correction. Right? Okay. Fine, I think we should stop here. Okay, we have the data. I've already explained what is end correction. Now next time we will solve the question. Alright, or else you are going to get very late for the chemistry. Goodbye.